Hello everyone, my name is Hussein, Vice President Space Systems at Thornton, Tomasetti. I would like to thank Aerospace Corporation for having me here today, talk about some of the work we've been doing in the area of assuring trust in advanced autonomy for space traffic management. We're all aware that the satellite population is growing and growing very rapidly. Associated with this growth is also a growth in mission complexity. If we are to have a future STM system that is able to handle such a large satellite population and mission complexity, the operators that would be required to manage such a future system can become quite prohibitive. Many of the STM functions, on top of all of that, really would benefit a lot from improved timeliness, which almost always means that we would need to transition those functions to orbit. This transition to orbit implicitly implies the utility of autonomy capabilities. Specifically, what I'm talking about here today is a subclass of autonomous systems that I'm referring to here as advanced autonomy. Specifically, advanced autonomy is any machine intelligence capability that goes beyond rule-based autonomy. A very good example is any one of the many techniques that rely on neural networks, for example. But why advanced autonomy? So to date, especially for space systems, we primarily rely on rule-based frameworks that are limited by the engineers, what the engineer can imagine and know based on experience at design time. This really limits what we can do with a satellite with autonomy technologies, and we think that we can do a lot better by leveraging some of the advanced autonomy capabilities that go beyond rule-based autonomy. However, there's a big caveat. Advanced autonomy um, almost always lacks assurance of performance at design time and lack a general sense of explainability. So that's the dilemma that we have. These tools are very powerful, but we're not always guaranteed to know how they're going to behave or act when they are operating on their own. So this gives rise to this notion that we need to figure out a way to take advantage of these unique capabilities that advanced autonomy offers while assuring at as a bottom line safety. And when such autonomous systems behave, we also would like them to behave in some optimal way and possibly one day with a level of agency. Those three properties are things that are at heart of the research and development work that we've been doing over the last few years, starting with safety, implementing some autonomous solutions that are centered in and around optimal performance. And finally, we also have a paths forward for how to enable an autonomous systems to act with some level of agency. For example, when a fault occurs, especially if it's a software fault, for the autonomous system to go in, adjust some aspects of the software in order to deal with a new reality, a degraded environment, a degraded condition, a failure, and so on. All right, so the rest of the talk is broken down into two quick pieces. One piece is focused on assuring trust in advanced autonomy technologies, as per this discussion I just made, this presentation just made. And then the second part is going to focus on trust enhancing autonomy technology. There are a class of technologies that are autonomous, that are already trusted, that we know very well how they're going to behave and operate. However, they themselves enable trust in an overall autonomous system framework. And I'm going to talk about what I mean specifically about that. For the first, I'm going to focus on a use case that has been a high priority of our work, which is the notion of the problem of fault detection, identification, and recovery using advanced autonomy. For the second part, it's centered in and around the concept of distributed ledgers. and how that can be applied for a problem that is very core to any space traffic management system, which is collision resolution. All right, so for FDAIR, Advanced Autonomy for FDAIR, this is work that we did with Virus Research over the last few years, and our customer has been the Air Force Research Lab in Albuquerque, New Mexico, Space Vehicles Directorate. All right, so but I'll step back just a moment here and talk not about space systems, but about general autonomy for general platforms. Uh, Best practices today, the state of the art today for aerial and terrestrial applications, autonomous vehicles applications. So for those systems, typically you have two styles. And by the way, everything I talk about here is focused around the guidance navigation control subsystem. Similar discussions can be had about other aspects of an autonomous system. But however, here I'm focusing primarily on the guidance and navigation control subsystem. All right, so typically we have two classes of controls or control systems that fly as a vehicle. One is what we would describe as a trusted control system. A trusted control system is a system that has been VNV'd to our heart's content at design time. And we know fairly certainly how it's going to behave when it is in operation. Now, those systems, the reason why we can VNV them to a satisfactory extent is because they tend to be simpler and their capabilities tend to be a little bit limited. Now, for us to employ other control systems that are more advanced, the more advanced class of control systems typically lack these, like as I mentioned earlier, testability and the assurances for how they're gonna perform in operation. So we have those two control systems, and really what we're trying to do here is to balance the utility of both. So what we would have is then a monitor that would be monitoring the advanced control system as it's running in flight, and if it starts to recognize that we are departing away from a safe region of operation towards an unsafe region or mode of operation, it pauses the advanced control system, switches to the trusted control system until we are back into the safe region, and then you repeat. Now, for space systems, the story is a lot simpler. Today, we really, because we're so conservative in the space environment, that we really only fly trusted control systems, things that have been vetted to our heart's content at design time. We fly them, and even then, sometimes errors do occur, faults do occur, and unexpected environmental conditions do occur or operating conditions do occur. And that point, really the only option is when we notice that is to save the satellite, put it in a safe state until we get some further instructions from the analyst on the ground on how to proceed. That we think is very inefficient because we believe that there is a lot of safing that happens and there's a lot that we can do without having to automatically go to safe mode, extend the life and operation of a satellite, and this is the space that we are exploring and trying to kind of squeeze the most service out of a satellite without having to continuously go to safe mode operation whenever anything goes wrong. Without getting into a lot of the technical details that can go into this, we've applied this concept to the FDIR problem, specifically adjusted a lot of aspects of the runtime assurance framework for space systems, and where we leverage advanced autonomy, things like machine learning, hierarchical reasoning, and other technologies from machine learning and AI that help us detect, identify, and recover from faults. And yet, of course, we know that some the systems are going to find themselves sometimes not making the right decisions. So we've adjusted the classical runtime assurance framework so that we enable to leverage advanced tools and techniques for the FDIR problem set And then the decision here is not to just whether to save or not save satellite, but whether to resume operation because everything is fine and normal, or resume operation because even though things are not normal, we are under abnormal conditions, we still think that there is enough guarantees that the system can proceed safely even under degraded conditions, or if such a determination is not warranted, then we do save the satellite. So this really is a big bulk of the work that we've been doing over the last few years. I'm going to spend the last 3 minutes on another topic that I've been exploring, working on over the last few years, and have had many discussions with Professor Moriba Jah over at UT Austin. And likewise, part of this work today is done in collaboration with IBM, with the IBM team, the cloud services team. All right, so specifically I want to explore using distributed ledgers, blockchains, otherwise known as blockchains, for collision resolution. Quickly, first, a distributed ledger is really a fancy term for a database that has some peculiar features. First of all, it's decentralized, it's distributed among many users, and it's immutable. It's immutable because not because we set up software that we like rule-based autonomy that we would control the software such that nobody is allowed to change data. No, even if somebody tries to change the data, they can, but they're not going to be able to change it entirely throughout the entire data throughout the entire distributed database. And there's no central authority that can go in and adjust all the databases all together to tamper with the data. You can have system administrators, but no single system administrator can have the authority or ability to change data on the ledger. Distributed ledger could be permissionless or permissioned. Permissions essentially means open source. Anybody can download software and be part of that ecosystem. Bitcoin is a very good example of that. Permissioned is a closed system and is only those who have been vetted and admitted into the ecosystem are allowed to operate within it, which we think is, me personally think that this is the more relevant framework for global transparent space traffic management. All STM data are then automatically synchronized through a consensus framework. That's how we achieve immutability and how we distribute the data among many users so that we all have a copy of the database as it exists. And it stores two types of entities. One is data and information, which is useful for data and event provenance, and also stores what we would call smart contracts. A smart contract, very briefly, this is a description, is a self-executing contract that really encodes a participant's business model. So if you are a space traffic management commercial data provider, the smart contract will describe anything from your subscription types to the pricing and to the actual execution of a negotiation between yourself and a data consumer. Now, let's take that back to the particular more forward-looking application, which is the autonomous collision resolution. We think smart contracts and distributed can be used to resolve a collision situation on orbit between two autonomous vehicles. The framework that we envision is going to be opt-in, vetted, permissioned, and it is going to be a framework that enhances and improves transparency, confidence building measures for autonomous collision negotiation resolution via the smart contract framework. And when a resolution is achieved between two objects on orbit, that transaction gets documented on the DL. So the system, here's a quick graphic for how we envision the system. We have the on-orbit, the segment, the on-orbit segment. We have the ground segment. Some participants in the systems, or some of the existing space system players would have a distributed ledger smart contract capability. Some won't. Some are going to be debris objects. That ecosystem, we have a path forward, and we see how that can be very valuable for a future STM framework. On the ground, we can have research institutions as well as national and international agencies. Let me move quickly here to an application that the most nuclear aspect of scenario is when you have two satellites on orbit, each having a smart contract. Both of them recognize that there is a collision imminent. They exchange messages, they acknowledge the collision, they're in agreement, then they negotiate who's going to move and who's going to pay, and how you're going to move and how much you're going to pay. The agreement is achieved, and then that gets stored on the distributed ledger. The same framework would be very valuable even if one of them, of those interactants, is not equipped with a distributed ledger technology on board. In that case, the one that does can then store the analysis it did, the reasons it did it, and the fact that it maneuvered and how, and then that gets, would be a record in case there is further investigations about the incident. Then we know who did what and how. This is the future, but we can do so much with distributed ledgers. Anything from basic registration to ephemeris sharing and updating. As I said, reporting, even just reporting, not autonomous collision avoidance, just reporting of potential collisions. And of course, a classical example is STM SSA commercial data marketplace, something that I've explored for the last few years, and I know other organizations have made some really good progress on this problem for the DoD. Forensics inquiries. So now that everything is provenanced, then we can go back and look at what what happened when, and which it could be very valuable from an insurance, for example, or legal perspective. And of course, this data, you can have other players interacting in the framework for research and development purposes, or for both by research institutions as well as international and national space and regulatory agencies. Really, what we envision here is an end-to-end distributed ledger framework for a future space traffic management system. Thank you so much for your attention. Please don't hesitate to reach out for any questions.